Hello students, now we are going to look at question 14 of the reaction mechanism tutorials. You might find question 14 a little bit challenging because it's the usual kind of question where it's being asked in university. Not much clue is given to you. You are just given the starting material and the products, and you are expected to draw a mechanism leading to the products. But rest assured that such questions will usually not be asked in H3. If it's ever asked in H3, it will be heavily guided. So I hope you do not get too stressed out over this question. And that also explains the point why we want to come up with this particular review, so as to explain to you the thought process in getting the answer, and also along the way give you a little bit of clue on if this kind of question is ever asked in school assessment, how will we make it such that it is accessible to most of you guys. So I will just go through each of the parts slowly, and you will realize that most of the reactions we covered are familiar to you. The only difference is that when you put them together, it gets really challenging. So for 14a, right, we have a structure on the left. If you look at the functional group, it has a methoxybenzene. There's a ketone and an epoxy group. And epoxy is essentially a cyclic ether, which is a 3-membered ring. So this is the epoxy group. And then on the right hand side, you have a phenol, as well as O-methoxy and a phenol ring right below here, which is just represented with a pH. And you are provided with simply a catalyst. And this is something you are not familiar with, but in the tutorials, your tutors will have told you that this is a strong organic acid. So this organic acid is known as paramethyl sulfonic acid. Sulfonic acids are stronger acid than carboxylic acids, simply because when the H is being lost, the O minus, the O minus can be delocalized into one of the two sulfonyl oxygen. So it can be delocalized. So in that sense, the extent of delocalization is expected to be greater, for the O minus. So that which means the conjugate base is more stabilized, as what you have learned from the chapter on acid-base equilibrium in H2, and because of that, it can behave as a strong organic acid. Sometimes you might be wondering why don't we just use our usual acids, mineral acids. A simple reason is the advantage of having an organic acid is that it can mix well with the organic reagents we are dealing with. So that's just a simple idea which we thought we just want to tell you. So we have a strong organic acids, and we have epoxide on the left hand side. So I hope it does make sense to you, and we have gone through several of this in the tutorials, that the first step usually involves the protonation of the epoxy oxygen. Because that will be the weakest link, because the epoxide group it's experiencing high ring strain, so it will want to ring open where possible. But before we perform the protonation step, you might just want to number the carbon. So if I'm going to number the carbon, then we'll slowly draw towards the product. So the key carbon to number will be these two: 1, 2, 3, 4, just the 4 of them. And you recognize that they are part of the structures. And if you just number the same carbon on the right hand side, it will be 1, 2, 3, 4. So without going into details, you know that a new bond is being formed between the phenol ring, which is 4th position relative to the methoxy group, and carbon number 4. So that might remind you that some form of electrophilic substitution might occur. So in that sense, if you want to propose a mechanism, the first step is likely to be some form of electrophilic substitution. and then followed by losing of water, because if you look at carbon 1, 2, 3, and 4, there's only one oxygen left, which is here. Yeah. But for my starting material, I have 2 oxygen, so that means that one of the oxygen must be lost as water. Okay, because you cannot just lose oxygen like this. Okay, yeah. So with the ideas in mind, we can envision that the first step involves the protonation of the epoxy oxygen. So I will just represent the protons as a H plus. Okay, I mean, if you want to, you can show the arrow pushing from the lone pairs of electrons on the epoxy oxygen all the way to the H here, the protonic hydrogen here, but you don't have to. Okay, yeah. Then after protonation, I'm just going to draw the protonated epoxide. Okay, yeah. I'm going to purposely draw it in such a way that it will resembles the structures on the right hand side. Okay, so I'm just going to showcase like this. Okay, O methoxy. Okay, and then an O here, so that's 1, 2, 3, 4. Okay, and then a pH. Okay, and then I'm going to show the epoxy oxygen with a plus charged. Okay, so now if I number the carbon, you notice that it now look in the right position for electrophilic substitution to take place. Yeah, so remember that for electrophilic substitution to take place, we will want to push electrons from the electron source all the way to the electron sink. The electron sink here is the protonated oxygen of your epoxy group. Electron source, of course, will be your benzene ring. But for your benzene ring, there's a O methoxy. There's a methoxy group over there, which is electron rich. So if you push electron density all the way from the source to the sink, it should look something like that. So this is a source. I push, I form a pi bond, and then I pushed. Okay, and then I push, and then the electrophile ring opens. Okay, yeah. So I'm just going to draw again. Okay, so I'm going to draw the phenol ring. Okay, and then like this, the O methoxy is like this with a plus charge. Okay, and then now I already formed the 6-membered ring, so I can simply just draw this out. This is the pH, OH. Okay, and then a double bond O. Yep, and that's it. Okay, yeah. So the next step would be regenerating the aromatic ring for the left hand side, for the ring on the left. So okay, so again, as per all electrophilic substitution, I expect the protons to be lost. Okay, what can you use to gain the protons? Probably the conjugate base of the para-methyl sulfonic acids. Okay, but I can simply just drop off the proton if I want to. So if I make my life easier, it will be like this. Okay, like this, and then I just push back to the electron sink, which is the O methoxy. Okay, and then eventually I will gain back the aromatic ring. Okay, like this. And then this is the MEO, and then I'm just going to draw this out. Okay, and then a phenol ring here, and then an OH. Okay, yeah. So the next step is how can I lose a water molecule? Okay, so most of the time a water molecule is lost if the hydroxyl group is protonated by the strong acids, and then yeah, then it can be lost accordingly. Okay, so that's usually how we can lose the water molecules. Okay, or lose the OH as a water molecule. Okay, so we can do that as well. So I'm just going to draw in the lone pairs here, and then maybe put in a H plus. Okay, and then I use the purple ink to draw the arrows. Okay, so I'm going to protonate this. Okay, and then OME. Okay, so the rest are details which you can fill in yourself, but for simplicity, I'll just draw everything in. Okay, so that no step is lost. Okay, so this is H2 plus. Okay, so right now there are 2 potential positions for the H plus to be lost. One is over here and the other one is over here. Okay, so which one is preferred? If you recall from question 11, alpha beta unsaturated carbonyl, it seems to be a structure that is quite stabilized. Yeah, so with that idea in mind, I do expect this H plus to be lost, the alpha protons. So in this case, I'm just going to lose the alpha protons, and then I'm just going to kick out the water molecules, okay, at the same time. Okay, or you can do it like an E1 fashion. Okay, you kick out the water first and then lose the H plus. It doesn't really matter. Okay, so a minus a H plus. and then minus a H2O. Okay, so from here I'm going to get the alpha beta unsaturated carbonyl. Okay, and then with a ketone here. Oh, sorry, the carbonyl and then a pH here. Okay, then some of you might be wondering, how can I produce the phenol? This phenol over here. As all of you know, with the strong acids, the carbonyl oxygen can also be protonated. Okay, so I can let the carbonyl oxygen be protonated like this. Okay, and then in the process, you can see that the shape is coming out. And then I'm just going to need one final step, okay, to form the structure. Okay, so that's pH. Okay, and then there's a H here. Okay, so I hope you can see from here. So after that, I'm just going to push all the way to the electron sink. Okay, form the pi bonds between carbon 4 and 3. In case you forgot the numbering, 1, 2, 3, 4. Okay, form the pi bond between carbon 4 and 3, and then form another pi bond between carbons 1 and 2, and then now the CO pi bond breaks towards the oxygen. Okay, and then finally I'm going to end up with this particular phenol. Okay, MEO, and then like this. Okay, and then pH, and then OH. Yep. Some students will ask, can there be other variations? Okay, so you might be wondering, what kind of variation can I have? So for example, some of you might not recognize that I need to form the alpha beta unsaturated carbonyl. You might form a CC pi bond between carbon 3 and 4 first in this particular step. So let's say, what if you form a pi bond first over here instead of over here? Is that okay? I guess it should be fine. But as I mentioned to you earlier on, if this particular way of arrow pushing is required of you, then we might give you clues such as the alpha beta unsaturated carbonyl, or we don't have to use the term alpha beta unsaturated carbonyl. We can just say the CC pi bond conjugated with the CO pi bond is known to be a more stable system as compared to, let's say, a CC pi bond conjugated to a phenol ring, for example. We will give you a clue like that. So upon reading that clue, then you might recognize that this might be a better product as compared to forming a CC double bond first between carbon 3 and 4. Okay, yep. So there can be some other variation. Of course, it's open to interpretation. There is no absolutely right or wrong answer for mechanism. I think the bulk of it is we are just proposing a reasonable mechanism. The idea here is reasonable. We're not looking out for the absolute mechanism, because you will never know what the absolute mechanism is. Okay, yeah. Then with that, we can move on to part B. Okay, part B is something that is familiar to most of you. The reason is most of you might have seen something like the reverse happening. To get this is what we call an Eno ether lah. In case you want to know the name, this is called Eno ether. Okay, so what exactly is an Eno ether? So basically from question 11, you know that an Eno is, you have a CC double bond, and then the OH is bonded to the sp2 hybridized carbon of the CC double bond. And then an ether is a linkage where the oxygen flank is being flanked by two R groups. Yeah, so a combination of that will be an Eno ether. Okay, an Eno ether is like a mask form of an enolate or an eno, because it's the more stable form. Yeah, so because of that, you preferably you should be able to recognize that the beta carbon, or okay, maybe I can just number as carbon number 2, right, is known to be nucleophilic because the lone pairs of electrons here is likely to be pushed back to form the CO double bond, and then the pi bond is likely to be nucleophilic, and it's likely to attract, let's say, a H plus from a strong acid like HCl. Yeah, so that is something which you probably want to recognize as the first step. Okay, so I'm just going to draw an equilibrium arrow, because the actual fact is that the whole reaction here is existing in equilibrium. Okay, and then yeah, so I'm going to have this with a plus charge. Okay, something like this. Okay, of course, if you recall what I mentioned earlier on, right, I highlighted that the reverse reaction is something which quite a number of you have seen, right? The reason why I said that is because the reverse reaction will involve the protonation of the carbonyl oxygen first. Okay, so let me just show you. Protonate the carbonyl oxygen first, and then I will just equilibrate, and then the protonated carbonyl oxygen is then susceptible to nucleophilic attack by the methanol. Okay, something like that is what you might be familiar with. Okay, remember an idea known as the principle of microscopic reversibility. That means that whatever mechanism you propose, it should be able to, when you work backwards in the reaction step, it should also be a reasonable mechanism as well. Okay, so I'm just going to write that in, and then this is a OH. Okay, and then this is a OMe, so O and then Me with a H plus here, something like that. Okay, so something like that is it should be something that is familiar to you. Okay, yeah. But I will not continue the reverse step, because later on you'll realize that I will be able to reach what I have drawn here in purple, okay, from blue. Okay, so once I form this particular unknown, right, from the eno ether, you know that there's a H2O as a nucleophile. So and the carbonyl oxygen now takes on a positive charge, so it will make the carbonyl carbon more electron deficient. So because of that, I expect the poor nucleophile such as water will be able to perform a nucleophilic attack on the carbonyl oxygen, sorry, on the carbonyl carbon, and then the CO pi bond will now break towards the oxygen. Okay, so when that happens, I'm going to get something like this. Okay, and then I'm going to get OH, and then with a H here with a plus charge, and then over here I'm going to get OMe. Okay, OMe like this. Okay, are you able to recognize that the structure I've drawn in blue over here and the one in purple seems quite familiar to you? They are quite similar. So that means that in order to get from the purple, okay, sorry, this should be an equilibrium arrow, so just ignore me. Okay, this should be an equilibrium arrow. Okay, so from the blue to the purple structure, all I need to do is just to perform what we call an intramolecular proton transfer. Okay, so like this, and then I should be able to get a purple structure. And then after that on, from the intramolecular proton transfer, I will be able to get a purple structure. And how do I move on to give me the structures above? Okay, because what I've drawn here is to push the arrow backwards, but now I want to push it forward. Okay, what should I do? Okay, so what you could do is, I'm just going to highlight like this. Okay, I'm going to draw the lone pair. The lone pair of electrons from the OH will just come in to form the pi bond, and then I will kick out the alcohol group. Okay, so once I kick out the alcohol group, okay, I'm just going to erase this to make it not so confusing. And then when I kick out the alcohol, plus MEOH. Okay, and then what I need to do now is I need to erase this. I need to draw out the sigma bond. Why do I need to draw out the sigma bond? Because I need to show the breaking of the OH bond in order to generate back the aldehydes, and at the same time the H plus, so plus H plus. Okay, so I should be erasing this. Yeah, so if you take note of what I said to you earlier on, using the principle of microscopic reversibility, you notice that the reaction can go reversed, and everything else will work. Okay, so I hope this basic idea will help you appreciate how question 14b works. Yeah, 14b will be quite a common question you expect in H3, but it will not be asked in the way we ask you in this particular tutorial. Usually you'll be guided with a lot of preamble questions, and then you're supposed to do quite a bit of work before you draw the mechanism lah. I mean, in terms of explanation, etc. Okay, so with that, let us move on to 14C. Okay, so for 14C, it looks like quite an intimidating question. Yeah, but it is not. Essentially, you should be familiar with... Okay, whenever I say you should, that means that upon doing the earlier tutorial, in this case, question 11, may I refer you to question 11 from your tutorial. Okay, you should be able to draw for me the mechanism going from two equivalent of propanone all the way to the alpha beta unsaturated carbonyl. Okay, it should be done quite easily. Okay, if not, then maybe I can just illustrate to you over here. So remember that in the presence of a base, the alpha protons will be removed because the conjugate base is resonance stabilized, or it can be delocalized into the carbonyl oxygen. So with that, then your first step definitely involved the deprotonation of the alpha protons, and in the process I'm going to form the enolate. Okay, so this is known as an enolate. Yeah, so enolate. Yeah, and I mentioned in question 11 that if you are not so comfortable in drawing the enolate in this particular form, it is perfectly fine for you to represent it like this. Yeah, because I think for most of the students, it is easier for you when you represent it this way to show connectivity, to understand which carbon is bonded to which carbon. Okay, I'm going to show you next, so you can let me know if that is easier for you. Okay, so so the next step, right, will involve some form of nucleophilic addition. Okay, so I'm just going to show you another ketone, propanone in red color, so it's easier for you to picture. So if I'm going to number that, that will be 1, 2, 3. Okay, 1, 2, 3, and then 1, 2, 3, and then this will be 4, 5, and 6. Okay, so what's going to happen here is that for the enolates, I'm going to push back to form the CO pi bond, and then carbon 3 will be the nucleophilic carbon, which will then attack carbon number 5 via a nucleophilic addition-like reaction. And then because it's nucleophilic-like addition, I'm going to push the electron density all the way to the carbonyl oxygen. Okay, so with that, I'm just going to draw for you the structures. Okay, so it will look something like this. Double bond O. Okay, and then going to form a new bond, and then after that, I'm just going to show you the OH here. Okay, and then like this and like this. Okay, something like that. If I'm going to number the carbon, there will be 1, 2, 3, 5. Okay, so this will be carbon number 5, and then 4 and 6. Okay, you notice that if I push the electron density directly from the lone pairs of electrons on carbon number 3, it is easier for you to see that the nucleophilic addition occurs between 3 and the carbonyl carbon 5. Yeah, but if I draw the enolate form, it is more difficult for beginning students. Yeah, so I really leave it to you how you want to present your answer, because it doesn't really matter as long as you are able to understand what exactly is going on. Okay, then you were told that further heating results in the loss of the OH group. Okay, so how is that going to happen? Okay, so that usually happens in some form of what we call first order elimination conjugate based kind of mechanism. Yeah, but it is not exactly required of you to know how to draw it, at least for the even for the H3 curriculum, unless you are being given other data. Okay, so what exactly is going to happen is again, the alpha protons is acidic, so we have a hydroxide. Okay, and then I'm going to remove the H here. Okay, most of you will simply just draw out the steps like this. Okay, you will simply just kick out the OH minus. Okay, but this is not a good way to draw this particular mechanism, because it because there is a stronger electron withdrawing group which is at the carbonyl oxygen. Okay, so the actual mechanism should be the CH bond will break heterolytically and then form back the enolates. Okay, at carbon number 2 and 3, and then O minus at the carbonyl oxygen. Okay, so what's going to happen is that I'm going to have an O minus here, and then a CC pi bond. Okay, and then I'm going to have the rest of the structure here. I'm going to show in red. Okay, and then in order for me to eliminate out the OH minus, I'm going to push back the CO pi bond, and then the CC pi bond will move to the alpha beta position, which is carbon 3 and 5, and then I will now kick out the OH group as a OH minus. Okay, so if I'm going to number the carbon 1, 2, 3, 5, 4, and 6. Okay, I think from here you can see that I will end up with this particular structure. Okay, so I hope it's not too surprising like this. Okay, yeah. Then after that, you are being introduced one more propanone, and this is the slightly more difficult step. So because it is the slightly more difficult step, so perhaps I'm going to guide you a little bit over here. And as I mentioned earlier on, you will probably want to recognize that for H3 assessment, if we ever test this question or give it to you as a test in any of your exams, then we will definitely guide you along the way. You will not be thrown and then asked to answer the questions. Okay, so that is the promise you can have from us. Okay, now I'm just going to highlight the structural features. Okay, you notice that this portion, right, and then especially with the 2-methyl group, right, actually the 2-methyl group appears here. I hope you recognize that. Okay, and then the remaining portion is actually over here. Yeah, so that means this particular 3 carbon, it's now here. Okay, yeah, so if I'm going to number the carbon, I'm going to follow the same numbering. That will be what, oops, sorry, I'm going to number the carbon. So that will be 1, 2, 3, okay, and then this is 5, this is 4, and this is 6, right? Yeah, so I'm just going to do the same numbering, 6, 5, 4, 3, 2, 1. So if I call this 7, 8, 9, so this will be 7, 8, and 9. Okay, so I hope you are able to see how this thing can be derived. Okay, so carbon number 9 and carbon number 5 will form a bond, as well as carbon number 8 and carbon number 1. Okay, and you were told that the enolate is probably formed between the propanone and sodium hydroxide first. Okay, so with that, we know that this is the enolate, right? We know that this is the enolate. So we do not attempt to redraw the mechanism forming this enolate because we don't want to waste time. Okay, so I will straight away draw out the enolates, in this case in orange. Okay, so I'm just going to draw the enolate straight away, O minus. Okay, so that we can continue to draw the mechanism and then get the final answer. Okay, and then so that you can see how the final answer can be gotten. Okay, so 7, 8, and 9. Okay, yeah. So what exactly is happening here is that I'm just going to push the arrows for you to see. Okay, so lone pair of electrons on the enolate will now form the CO pi bond. Okay, and then after you form the CO pi bond, carbon number 9 is the nucleophilic carbon. Then it will attack carbon number 5 in what we call a conjugate kind of addition, and then I will push all the way to the electron sink, which is the carbonyl oxygen. Okay, yep. So from here, I'm just going to reorientate it such that it will look like the one above, so that it's easier for you to make reference because I know that earlier on my orientation is a little bit weird. Okay, so I'm just going to orientate it like this. This is the double bond oxygen, then this is the carbon, and then 3, and then I'm going to have carbon 4 and 5 here. Okay, just going to orientate it in this particular manner so that it's easier. Okay, and then I'm just going to have the carbonyl group like this. Okay, then because it's a conjugate addition, is like this, and then I'm going to have this and then O minus. Okay, so if I number the carbon, that will be 1, 2, 3, 5, and then 4, 6, and then 9, 8, 7. Okay, like this. Okay, so maybe you can double check to see whether it makes sense or whether I've made any mistakes. Okay, then with that, then I can reform the CO pi bond, and then I will then just grab H from H2O. Okay, and then I will regenerate the OH minus. Okay, yeah. So from here, then the next step, I'm just going to redraw the same thing. It's not going to be anything fanciful. Yeah. I'm going to use different color so that you can see. Okay, I hope the color coding helps, because sometimes the reason why students can't do the question is because they get a bit confused with the colors, with the not color, sorry. They get a bit confused with the carbon counts. Okay, so once you get the number of carbon correct, I think everything else can be followed quite easily. Okay, then next part is how can we form a CC double bond between carbon 1 and 8. Yeah, that is probably one of the main question that some of you might have. Yeah, we can easily form a double bond between carbon 1 and 8 by a nucleophilic kind of addition reaction followed by an elimination. Okay, so we can do that. That is not something which is unusual, because the first step of the aldol addition is to form the aldol, and then this is followed by elimination of H2O to give us the alpha beta unsaturated carbonyl. So again, we can do the same thing to obtain the new alpha beta unsaturated carbonyl. Okay, so yeah, let us do that very quickly. So there's an H here. Okay, so I'm just going to deprotonate. Okay, remember that when I deprotonate, you can either form the enolate or add by pushing all the way to the oxygen, or simply show the short form. So as I mentioned, to us it doesn't really matter as long as you get the answer. Okay, yep. And then from here, I'm going to just push the electron density, and then I'm going to do a nucleophilic addition kind of reaction. Okay, yep. And then if I'm just going to showcase to you what exactly is going to happen, then I think it will look like this. O here, and then like this. Okay, and then this will be the orange one. O minus, like this. Okay, yep. Then just to double check whether it makes sense. So if I'm going to number the carbon, I think I need to follow the numbering on top. So that will be 1, 2, 3, 5, 4, 6, 9, 8, 7. Okay, so yep. So the rest are details. I think you can fill in yourself, but just to make it more complete, again, I'm going to remove a proton from H2O. Okay, like this. And then after that, I'm just going to draw in the ring, and then like this. Okay, so like this, like this. Oops, like this. And then the one in orange, like this, OH. Yep. So again, we're gonna show you first order elimination conjugate base. I'm just going to push all the way to the carbonyl oxygen. Okay, and then after that, I'm just going to eliminate out the OH minus. Okay, so like this. Okay, like this, like this, like this, OH. Okay, and then I'm just going to eliminate out. Okay, form the CO pi bond, and then alpha beta unsaturated carbonyl, kick out the OH as a OH minus. Okay, so that will give me my products, which is drawn over here. Okay, yep, so these are the steps which you could follow in order to get the answers. Yeah, so again, not to be afraid in exam if you are ever required to go through so many steps, which I doubt so for H3, because H3 is not a module on drawing mechanism. Okay, we'll give you some clues so that you can start somewhere, and then you will stop at some intermediates. Yeah, not to worry. Okay, yep. So next, we're going to move on to part D. This question is quite similar to the iodoform test. Okay, so in fact, it's almost exactly the same. So if you are able to draw the mechanism to the iodoform reaction, then drawing part D, the answer to part D is not going to be a major issue. Okay, so I'm just going to revise a little bit on how to draw out the mechanism to the iodoform reaction. Okay, I'm just going to use the space above. So in order not to confuse things, I'm just going to erase some parts of this so that there's a bit of a space here on the left hand side. Okay, so yeah, I'm just going to show you how to draft out the iodoform reaction. Okay, yeah. So for the iodoform reaction, right? Basically you have a methyl ketone. So I'm going to just draw a R. Okay, a methyl ketone, and then a methyl ketone consists of 3 alpha protons. Okay, on the methyl group. Okay. So for the iodoform reaction, right, what exactly is happening here is that the first step usually involves the deprotonation using the hydroxide anions. Okay, so as a base. Okay, and then you are going to form an enolate. Okay, so enolate will be formed like this. Okay, and then because it's an iodoform test, right, you also introduce iodine. Yeah, and then some form of electrophilic addition will take place. Yeah, and the iodine being highly polarized, or having a huge electron cloud, is highly polarizable. Yeah, so I can easily perform the electrophilic addition by reforming the CO pi bond, and because I have a very powerful electron source at the oxide, so I'm going to push back to form the CO double bond, and in the process I'm able to get what we call the alpha substitution, okay, with iodine. Okay, of course, plus I minus. Yeah, and then this is going to continue another 2 times. Yeah, because the presence of an additional iodine atom, right, yeah, will further stabilize the conjugate base being formed, or the enolates being formed. Yeah, so this will continue further, and then eventually, right, all the 3 alpha protons will be substituted with iodine. So I'm gonna have I here, and then I here, and then I here. Okay, and then when that happens, the OH minus can no longer remove the alpha proton. Then what is it going to do? So if I can't perform deprotonation, then it is likely that I will be able to perform nucleophilic addition kind of reaction. Yeah, so I'm just going to attack the carbonyl-carbon, and then the CO pi bond breaks. And then in the process, when the CO pi bond breaks, of course it has the decision to make is whether you want to perform the nucleophilic addition kind of reaction and then form a nucleophilic addition product where the sp3 hybridized carbon will have 2 hydroxy group, and you know that this is not going to be stable. Yeah, so remember that when an sp3 hybridized carbon contains 2 OH, right, something like this, right, yeah, the more stabilized form is to remove the H2O to form the C double O, because the C double O is a stronger bond as compared to the CO. Yeah, so because of that, nucleophilic addition kind of product is not likely to happen. Then the next step will therefore be eliminating out the CI3 as a CI3 minus. Yeah, you might also be wondering whether that is a good leaving group. Yes, that is a good leaving group because the negative charge, or the lone pairs of electrons on the carbon is helped to, the electron density is being dispersed by the presence of the 3 iodo group. Yeah, and you have a huge electron cloud to help charge dispersal. Yeah, so that is a pretty decent leaving group. Yeah, then because of that, I'm going to form the carboxylic acids. And obviously the carboxylic acid will not exist for long because the Ci3 minus will undergo acid-base neutralization reaction. Okay, and then in the process, I will form the carboxylate anion. Okay, so that's why in your iodoform test, the carboxylate anion is your byproduct, or rather, is your product, and then CHI3 is your byproduct, which is the iodoform. Yes, so if you follow the same logic, it works exactly the same way. And now it might be even easier because I have number one, the CH2 is being flanked by two highly electron withdrawing CO pi system. Yeah, so it will be highly acidic as compared to the other two H's on the other side of the molecule. Yeah, so these are the two H's that are the most acidic. Okay, so the first step definitely involve the deprotonation of the alpha protons, and then I can choose to form the enolates, so I can just push all the way to the enolates. Okay, so I'm just going to repeat the drawing because it's going to be quite cumbersome because you're going to repeat a lot of things. Okay, but nonetheless, I think as a form of revision, I think it helps. Okay, so I'm going to form the pi bond, and then I'm going to help to perform electrophilic addition on the Cl. Okay, and then in the process, I'm going to get one of the Cl in, okay, and then reform the CO pi bond. Okay, and not to forget, I have another alpha protons, and then because of that, OH minus will then attack the alpha proton, and then I'm going to push it back again. Okay, always remember to balance your equation with H2O. Okay, yeah, and then or you can just write it as minus H2O. Okay, and then after that, I'm going to do the same thing again, form the enolate with a O minus, and then a Cl here, and then a double bond O. Okay, and then of course the next step involved electrophilic addition kind of reaction again. Okay, attack the Cl. Okay, and then after that, I'm just going to the two alpha protons will now be substituted with the two Cl like this. Okay, the two Cl. Okay, and then after that, you might recognize that there is no choice. Okay, so no choice here, meaning that nucleophilic addition kind of reaction will take place. Okay, so the OH minus will then attack the carbonyl carbon straight away. Okay, it can be either of the carbonyl carbon, doesn't really need to be the one which I've drawn earlier on, but let us just be consistent. Okay, and then after that, what's going to happen here is that I'm just going to redraw this. Okay, with an O minus, and then an OH, and then Cl, double bond O. Okay, so now, what is your leaving group? Okay, so now your leaving group is actually over here. So this portion becomes the leaving group, this whole portion. Okay, yeah. So addition elimination kind of reaction has it that when I want to leave, when I want the group to leave, okay, so I should push all the way again to the electron sink, right? So technically I can simply just push to the carbon here. Yeah, but because I have an electron sink, which is the carbonyl oxygen, so I might as well just push all the way to the carbonyl oxygen. Yeah, which kind of serves its purpose, right? Because remember that I always emphasize in the tutorials that when we push electron density, we should push it from the electron source all the way to the electron sink. Okay, and then with a carbonyl oxygen, and then O and a H. Okay, and then right now I can perform what we call intramolecular proton transfer. I can perform an acid-base neutralization reaction. Okay, okay, maybe I should show it like that. It's easier. And then I should push it all the way to the carbonyl oxygen. Okay, so this particular acid-base neutralization reaction eventually will allow me to form the carboxylate anions. Okay, so I'm going to form the carboxylate anion here. Okay, and then like this, and then double bond O, and then 2 Cls, and then and a H over here. Okay, so I'm going to repeat the same story, or maybe I should just write this as CHCl2. Okay, just CHCl2. Okay, so I'm just going to we're just going to repeat the same story because there's a H here, right? Remember? So some form of deprotonation of the H should take place. Okay, so maybe a CHCl2 is not that good an idea, so we still need to draw it out. Okay, a H here, a Cl, and a Cl. Okay, so we're going to repeat the same old story. The hydroxides will deprotonate this. Okay, and then I pushed. Alright, and then after that, I'm going to perform some form of electrophilic light addition reaction again. Okay, and then I'm going to form the enolates. Okay, just Cl. Okay, and then I'm looking at CCl3 here. Okay, CCl3, like this. Okay, CCl3. Okay, yeah. Then what's going to happen next? I think all of you can guess. Similar to the other form, nucleophilic light addition reaction takes place. Okay, and then just going to have this minus like this. Oops, we have a O minus and then an OH and then CCl3. Okay, and then I'm just going to push out the CCl3. Okay, and then I'm going to end up with this. Okay, like this, and then OH. Okay, and then the CCl3 minus will then be able to abstract the protons via acid-base neutralization reaction, and then after that I'm going to push all the way to the electron sink, which is the C double O. Okay, so eventually I will end up with my product, which looks like this. Essentially is what we wanted you to draw, so that's CHCl3. Okay, so we'll do a double check above. Okay, it's exactly the same products as what we wanted you to draw. Okay, so I hope merely by just going through with you guys slowly, you can understand the mechanics behind drawing of the mechanism leading to the final product, and you realize that a lot of steps are being repeated. So it gets a bit boring if the question gets a bit lengthy, like for example, what we have shown you earlier on. Yeah, it does get really boring, and because it's basically addition, elimination, or rather deprotonation and then addition, and then deprotonation and then addition, and then addition, elimination, and then deprotonation, addition again, and then addition, elimination again. Yeah, so we are testing it the same skills. So do take note that for Cambridge kind of exam for H3, right, they rarely test the students the same kind of skills. Yeah, so that's why I said that all these are just tutorial practices. So in reality, for H3 exams, we highly doubt that they will ask you to draw mechanism using so many steps. Yeah, but as I said, it's good for practice because you get to get the hang of doing the right thing for arrow pushing. Okay, yeah. So with that, we'll look at the next portion, part E, which is a slightly more difficult part, or some students might not think that it's difficult. Okay, so we'll see how it goes. Okay, so for part E, right, first of all, I think it does help if we can number the carbon. Yeah, because the carbonyl, because I think number one is we need to look out for some structural similarity. So this portion is here, and then it seems to be quite similar to this portion. Okay, and then of course we have an OM, the methyl ester group here, like this. Okay, so the methyl ester could be over here. Okay, so what is being lost? The parts that is being lost is this particular group, or rather this group. Okay, and then epoxide is being formed. Okay, so with that, maybe it helps if we can again the same old boring story which you heard me saying over and over again. Number the carbon. So 1, 2, 3, 4, 5, 6. Okay, so we'll do the same thing. 1, 2, 3, 4, 5, 6. Okay, so what we could do is, I think number one, we have a methoxy group in methanol. So of course this likely to serve as a strong base. Okay, remember that we have an ester here. If I'm going to expand this structure, right, it will look like this. Okay, so we have a ester group here and then an OMe. Now, similar to a carbonyl group, ester group contains a carbonyl carbon and a carbonyl oxygen, which is also highly electron withdrawing. Yeah, so if we have a structure that is something like this, right, the lone pairs of electrons on the methoxy group can perform what we call an acid-base neutralization reaction, and to deprotonate the alpha protons to form the enolates again. Yeah, and the reason why we use methoxy, right, is so much so that if addition elimination were to take place at the ester functional group, we will still get back the ester, because the ester is a OMe, is a methoxy ester. It's a methyl ester lah, rather than something else. Imagine if we use ethoxide and ethanol, right? We might change the ester from a methyl ester to an ethyl ester, which is not desirable in quite a number of cases. Because we will not be able to get the product we want. We're going to get a scrambling of products, which is not something we are looking forward to. Okay, so with that, I hope you do recognize that whenever we have blah blah ester like methyl ester, then we use methoxide in methanol. If we have ethyl ester, we'll use ethoxide in ethanol. Okay, so with that, I hope you can see already. I'm just going to draw it over here. Okay, I'm not going to write it out in too fanciful a manner. Okay, so OMe. Okay, and then I'm just going to push back the electron densities. Okay, and then the enolate will then attack carbon number. So I think the choice now is yours. Should it attack carbon number 5 or carbon number 1? Okay, now I think there are a lot of decisions which needs to be made. Okay, so what do I mean by a lot of decisions which needs to be made lah? I think the first thing we might want to recognize is that does it really matter whether it attacks carbon number 1 or carbon number 5? Yeah. Okay. So of course at the end of the day it doesn't really matter if you try to draw out the mechanism lah. But in terms of steric hindrance, carbon number 1 is directly less demanding as compared to carbon number 5. Yeah. So because of that, we might just propose attacking carbon number 1 instead. Okay, you can try to attack carbon number 5 at your own leisure, and then you can see what you will get eventually. Okay, so because of that, I'm just going to redraw out the whole structures. Okay, so double bond O, and then this portion remains. Okay, and then okay, so this part, right, I'm just going to draw it in. The extra carbon, so this will be the Br, and then the CO2Me. Okay, because I already formed back the carbonyl carbon, so I don't really need to expand any more of the structures. Okay, so I think that will be fine. And then after that, what is going to happen is that I'm going to reform the CO pi bond, and then I'm going to deprotonate the methanol. Okay, to regenerate the methoxide, okay, which is what we wanted. Okay, so I'm just going to draw it out like this. Okay, so the rest are details which I will leave you to fill in. CO2Me. Okay, but not to forget, there's also another proton here. Okay, so which again is acidic, and then we can use it to push all the way to the carbonyl carbonyl oxygen of the ester. So maybe it might be wise to expand out the ester for this particular case. Okay, so just expand it out. Okay, and then the next step, we will probably use another methoxide to deprotonate this H. Okay, and then we just push it all the way to the electron sink, which is the ester, carbonyl oxygen of the ester. Okay, so I'm just going to draw it below. I think there's no more space here. Okay, I'm just going to draw it below over here. Yep, double bond O, and then O. Okay, and then okay, let me just do a quick check. Double bond, and then O minus, and then OMe. Okay, so the next step is probably something that is familiar, which is similar to this step where we protonate the enolate. Okay, we have to do that. Okay, like this. Sorry, we don't have to protonate the enolate because we need to continue with the conjugate addition. Yeah, my apologies. Yeah, because remember, we need to close up this ring. So carbon 6 and carbon number 5 needs to form a bond, right? Yeah, so we need to close up the ring. Okay, and then what am I talking about earlier on, huh? Okay, so I'm going to form back the ring, and then so what's going to happen is just going to close up this ring. Okay, with a O minus, and then O, and then like this. Let me just do a quick check. There's a Br here. Okay, and then this will be a CO2Me. Okay. Yep, that should be fine. And then after that, I'm just going to do the same thing. Yeah. To protonate the enolate. Okay, and to regenerate the methoxy. Okay, yeah, so with that, I'm going to, we are already quite close to the final structure. Okay, the Br and the CO2Me. Okay, now, maybe before we continue, right, can we just do a comparison? So what exactly is being lost at the end of the day lah? Okay, so you realize that there is an ester here. Okay, there are two esters in fact in my in the last intermediate I've drawn. So the esters are here, highlighted in yellow, and then this ester. And then you realize that okay, maybe I should use another color. You realize that the ester which I'm highlighting in red, right, is lost eventually. Yeah, so in order to predict how it is being lost, and then how come we end up with an epoxy group, right? It might be helpful to think of it as probably the ester I'm highlighting in red, right, will undergo what we call an addition elimination kind of reaction. Okay, and then in the process, the O is being kicked out as O minus, and then the O minus will then perform an intramolecular nucleophilic substitution on the quaternary carbon, resulting in the Br leaving as a leaving group lah. Yeah, and of course, if I look at it this way, it does make a bit of sense, because remember that this is a CH3, right? Yeah, so this is a O methoxy, yeah, which resembles what we have here. So can we try that out? So maybe we can try that out and then see whether we can get our final answer. Okay, so let's try. We can have a O methoxy. Oh, sorry. O methoxy group. Okay, and then O methoxy group, and then undergoing addition elimination. Okay, and then eventually what I'm going to end up with, OMe, O minus. Okay, O. Yep. For some of you who actually read beyond the curriculum, this reaction is known as a trans-esterification reaction. Yeah, so meaning from the ester we have over here to another ester, which is the methyl ethanoate. Yeah, which is this is known as methyl ethanoate, the one highlighted in red. Okay, yep. So this trans-esterification reaction will take place, and then okay, so I will reform the pi bond to form the methyl ester, and then I'm going to form an O minus here. Okay, and then to perform an SN2 kind of reaction. So this will be minus this OMe. Okay, and then I'm going to end up with something like this, and then O minus, and then CO2Me, and then Br, and then you will then undergo an intramolecular SN2 to kick out the Br. Okay, and then I will end up with the answer. Okay, which is like this. Okay, yep. So I hope it's not too daunting. Plus Br minus. Okay, of course the Br minus will then combine with one of the sodium to give us sodium bromide, which will then drive the reaction forward because the production of ionic compound generates a lot of heat. Okay, so I hope you enjoy this particular mechanism for part E, because it's like a combination of a conjugate addition, or rather formation of enolate, conjugate addition, and then deprotonation again to form the enolate, and then another conjugate addition, and then after addition elimination, followed by an internal SN2. So a lot of it are reactions which you should be relatively familiar with as you progress through your studies. Okay, yeah. So with that, we're going to focus on the last part. Yeah. So the last part has you are given a clue on how to go about drawing the mechanism. Okay, so over here we have triflic acids, strong Lewis acids. So basically same as pyromethyl sulfonic acid. It is likely to protonate the carbonyl oxygen in this case. So we notice that X, there's an amide functional group. Okay, so this is an amide. So the carbonyl oxygen is likely to be protonated. So maybe we can draw in the protonation step first. Okay, so the lone pairs of electrons are H, OTF. Okay, so it will then protonate. Triflet will be lost, which is fine. And then after that, you notice that essentially, right, because of the protonation, that's how I end up with an OH over there. Okay, yeah. So and the protonation helps to make the carbonyl carbon more electron deficient, so that some form of electrophilic substitution can take place. How do I know it's an electrophilic substitution? If you do a quick count, you'll notice that for the phenyl ring, 1, 2, 3, 4, 5, 6. The fourth position is still bonded to the nitrogen. Okay, but the third position is now being substituted by the carbonyl carbon. Okay, yeah, so I hope this is fine with you. Okay, then I'm going to draw out the protonated form with a plus charge. Okay, and then with an N here. Okay, and then some form of electrophilic substitution is likely to take place. Okay, so what's going to happen here is that I'm just going to draw the electrophilic substitution straight away. Okay, going to form the CO, the CO pi bond will break. Okay, and then eventually we are going to get a weird looking structure. Okay, so I'm just going to sketch the structure out like this, and then an OH. Just hang on for a while, I think, while I get accustomed to the. Okay, so 3 and 4, that's fine. 1, 2, 3, 4. Okay, so this will stay, and then Cl, and then yeah, so the plus charge should be here. Okay, yeah, so the plus charge should be here. Okay, so if I number the carbon, that will be 1, 2, 3, 4, 5, 6. Yeah, so carbon number 3 should be the one with the H where it's lost, and then after the H is lost, it will regenerate the aromaticity. Okay, so that's how the aromaticity is regenerated. Okay, yep. Then from here, I'm just going to continue drawing out the whole structure. Okay, I mean like this, and then the Cl, and then the OH. Okay, then after that, the remaining part will be the protonation step. Okay, because we probably need to protonate the lone pairs of electrons on this amines. Okay, it's likely to be basic as well because of the geometry. So a lone pair is highly available. Okay, and then eventually we'll end up with the protonated structure, which is like this. Okay, and then what is going to happen is that the OH should be here, and then you notice that oops, I think this portion needs a bit of needs to be drawn a little bit more clearly. Okay. Yep. And then you notice that the two fused 4-membered ring now sort of ring opens up, and then that's how I get back the amines. Okay, so what's going to happen here is that the lone pairs of electrons will then push to form a pi bond, and then the NH plus will then be a leaving group, but it doesn't leave because the other side is still bonded to the benzene ring. Okay, yeah, so because of that, eventually we're going to end up with something like this. Oops. N, and then with a H here. Okay, and then double bond O with a H plus charge, and then for Cl. Okay, so eventually the OH bond will break, and then you'll be deprotonated as a H plus, and then eventually I'll get Z. Okay, yep. So strange enough, question 14F turns out to be so-called the easiest because it's guided. You were given an intermediate. Yeah, but if it's not guided, then probably you can expect other form of mechanism which can be predicted. Some students actually predicted some of pericyclic kind of reaction, but we'll not go into details over here. Yeah, so with that, that's the end of the review to question 14. I hope you will find it useful in your revision.